Hello again and welcome. Today we're going to be looking at the new NanoVNA version 2 Plus. In the center we have the V2 Plus4, and on the right this is the V2 Plus, and on the left this is the original NanoVNA. Of course, all the specifications for these are available for free online, but I'd like to just highlight some of the major differences between these. I believe the original price for this Nano was around $50. I believe the V2 Plus4 was selling for roughly $130, and the V2 Plus is selling for $60. The LCD on the original NanoVNA is roughly 3 inches. That's the same for the new V2 Plus. You can see it probably is the same display. I haven't looked into it. We can see for the new V2 Plus4 though, this is a 4-inch display. The V2 Plus comes with a new stylus. Of course, for my original Nano, I'm just using this old stylus from a PDA. The original Nano used the fundamental frequency for up to 300 megahertz. After that, they start using the harmonics. So from 300 to 600 megahertz, they're using the second harmonic. From 600 to 900, they're using the third harmonic, and so on. The current firmware that's installed in this unit allows it to sweep up to 1.5 gigahertz. From my own experience, once you get above 300 megahertz, this unit becomes less useful. The V2 Plus is rated for 3 gigahertz, where I believe the V2 Plus4 is rated for 4 gigahertz. Both of these units can run in excess of 4 gigahertz. As a matter of fact, I see very little performance difference between these two units. Of course, the original only had 101 data points. This V2 Plus supports up to 201 data points, where the V2 Plus4 supports 401 data points. The original Nano, I believe, could send up 100 data points in roughly a second, where the V2 Plus can send up 200 samples in that same second. The V2 Plus4 can send up 400 samples in 1 second. So this unit is quite a bit faster. When you're using the remote control, both units support up to 1024 data points. All 3 of these units can be battery powered. They all have built-in chargers. The original Nano came with a battery. This is what it looks like when it powers up. I believe that you could buy these V2 Pluses with a battery. I chose not to purchase them that way. The V2 Plus4 uses an 18650. You have to take the case apart, and then there's just a battery holder in the back, and you can see I have one installed. This is what the unit looks like powered up. The V2 Plus would use a similar battery to what the original Nano does. I've got one inside of this right now. You can kind of see it through the case right there. This is an old cell phone battery. So I just soldered a connector onto that and plugged it into the board. And this is what it looks like powered up. These are the cables that were supplied with my original Nano. And these are the cables that were supplied with the V2 Plus. You can see these are roughly the same length. The new cables appear to be a higher quality. You'd expect that because the new Nano is rated to work at a higher frequency. Of course, they each came with their own set of cables, so this is the other set for the V2 Plus4. The V2 Plus4 also came with this USB adapter. The 2 V2 Pluses came with identical calibration kits. These come complete with a load, a short, an open, and a through. Very similar to what was included with the original Nano. Again, you have a short, an open, a load, and a through. This is the calibration kit that I've been using with my V2 Plus4. This is the original calibration kit, but with a few alterations. This is the short that was supplied with the original NanoVNA. This appears to be identical to what's being supplied now with the new NanoVNA Plus. The problem with these is that there's no real good way to hold the center pin while you're threading this in. What you would like to do is basically put a wrench onto the back side of this and then go ahead and tighten down the nut. So what I've done is I machined up this piece of hex stock, and then I've gone ahead and soldered that to the back side of the short. And now you can see I can turn the threaded nut while holding that center pin stable. Again, it's very important that you don't rotate that center pin. And of course there's better connectors that could actually be damaged by you rotating that center pin. This is the original through that was supplied with the V2s. What I don't like about this, you can see there's no flat. So again, the problem is, let's say I want to insert my load, and I go ahead and I tighten this thing down. I get to the end, I can't torque this thing. So normally what you're going to do is you're going to put a torque wrench on this, and you want to lock this through in place. But with this through, there's no way to do that. I've gone ahead and I've replaced the original through with one that I can use a wrench with. This is the load that was supplied with the original Nano. Again, we see that there's no way really to prevent that center pin from turning when inserting this. This is the load that's supplied with the V2 Plus. You can see now we can grab the back side of this and rotate the nut. A much better design, beyond being able to just hold the part to prevent the center pin from turning. If we plot the return loss all the way up to 4 gigahertz for this new load compared to the original, the return loss for this is much better. Of course, these aren't going to be as good as what you're going to find in a real calibration kit. So to try and improve on the return loss, I'd purchased some parts from Mini Circuits. These are an Annie. I borrowed a set of Agilent standards, and then I characterized all 6 of these, and I sorted them based on their performance. This one's the second best out of the 6. So this is what I'm actually using to calibrate the V2 Plus4. This is the SOLT standard that I built to work with the original NanoVNA. This is the short. Here's the load. This is our open. This is a 10 dB attenuator, and this is our through. These are the standards that I use with my HP network analyzer. You can see there's a male set as well as a female set. On the side here I have several other circuit boards. These are various capacitors and inductors that have been characterized, and I use these to validate my calibration. This is an older standard that I made. This also contains a short, open, and load. Of course, there's a benefit to using a circuit board like this on the right over something like this, because in a lot of cases I can mount the component directly to the circuit board. I essentially remove a lot of the measurement errors. My first vector network analyzer was made in the 1970s. That's an HP 8754A. That network analyzer has no computer, so everything is analog, but it had a storage normalizer that allowed me to connect it to a PC. So I do all the math using a desktop computer. That system supports the frequency doubler, so it can run up to 2.6 gigahertz. I've attempted to make measurements up that high and actually beyond. What I was finding is my homemade standards really didn't work very well once I got up above about 1.5 gigahertz. So over the summer I made another set of calibration standards. Those are in this box here. So these are my N standards. Here's the open, the short, and the load. These sections are coax. These are a set of TRL standards that I made. These are my 3.5 millimeter standards. There's a short, open, and then this one is a T-check. This is the other Mini Circuits Annie. This is the best one out of the group. These were 2 old microwave attenuators that I modified. The top one is a 70 millimeter 25 ohm Beatty standard, and my middle one is a section of airline. So both my 3.5 as well as my N standards have been characterized against a set of metrology grade standards, and then I take those coefficients and I upload them into the network analyzer. These new standards are a big jump up over what I was doing with the original circuit board. Again, I still find these useful for working below a gigahertz, but for testing things in excess of a gigahertz, this is now what I'm using. So while we're talking about calibration standards, I'd like to mention that there's a person named Mario Helmich that had helped me out with this. Mario had written some MATLAB scripts. What it allows you to do is you can characterize a set of metrology grade standards. Of course, we're talking about a lab grade network analyzer. Then you can take another set of standards, whether they're homemade or purchased, and you can come up with a set of coefficients for those based on the data that you've collected for your metrology grade standards. He's also made some changes to those scripts, and he's made those available to the public. So I just want to give him my personal thanks for helping me out with that. So I played with these 2 V2 Pluses now for a couple of months, and I've noticed a couple of problems. And the first major problem is that these don't support any kind of a narrowband measurement. So back when I made the videos using the original Nano, somebody had asked me about making a video showing how to make a crystal filter using this. So I ran some different experiments, but I never actually made a video demonstrating it. These are 2 of the fixtures. This one on the right is the one that actually works fairly decent. You can see there's a couple of attenuators on the 2 incoming ports and a couple of transformers to match the impedance to the crystal. And you would just plug the crystal into the fixture here. So when I was developing this fixture, I was comparing the data I was getting with the original Nano against using the same fixture on my HP 3589A. And believe it or not, the results were very close. I also tried 2 other techniques to measure the crystals, and all that data actually came in fairly close. So I ended up making a couple of crystal filters. This is one that's a 12 megahertz 10 pole. This is another one I made. You can see it's a 1.5 kilohertz bandwidth. It's a 6-pole, 3.68 megahertz. You can see in this one it's built with fixed value capacitors. There's our small inductor to match this to a 50 ohm system. So when I first received the two V2 Pluses, I was attempting to repeat a lot of the experiments I had ran with the original Nano, including measuring some crystals. And I noticed right away that both of these units were unable to make those measurements. They just don't have the kind of resolution needed to make this measurement. So if you're interested in playing around with something like crystal filters, the original Nano is going to be your best bet. I'd even go so far as to say if you're working below 300 megahertz, this is probably the better choice. If you're working above 300 megahertz, hands down, it's going to be these two units. Of course, I was running these things for hours at a time, and what I found is that this unit would hang. And when I say hang, essentially what would happen is it would stop communicating on the USB bus altogether. It's kind of odd because the PC didn't actually see the port close down or anything, so as far as Windows is concerned, the unit is still alive and active, but the unit fails to respond to any commands. The only way that I found that I could shake this thing loose is to power cycle the unit. Originally I thought that the problem was tied to the amount of data that I was bringing down. It appeared that the chance that it would lock up would increase based on the amount of data that I would send across the port. So it seemed more reliable at 100 data points, for example, than 400 data points. The more I ran into the problem though, I don't believe that has anything to do with it. Another thing that I thought about was maybe it had something to do with the USB port, maybe not being able to supply the power, and where this one I was running it with a battery, this one I was not, so that's the reason I added the battery. I also conducted tests where I removed the LCD, and none of that made any difference. I've looked at the circuit board under the microscope, all the soldering joints look good. It could be a firmware problem. I think the longest I've had this thing run is maybe 6 hours at a time. Typically it crashes somewhere around the 2 to 3 hour time frame. And again, to be clear, that's basically non-stop pulling data across that USB bus. Now, this V2 Plus 4, running these same tests, I've never had this unit lock up at all. So I would say if you're going to buy one of these new units, this is probably the one that you want to get. So again, I'm not normally using these units with the touchscreen. As a matter of fact, I've actually ran experiments with this particular one where I've removed the screen altogether. I literally could run my experiments just using the main circuit board. The main reason is as soon as you start communicating with these, the only thing that happens is the screen will display that this is running in USB mode, and that's it. So where the original Nano, you could actually use the LCD to monitor what was going on. These new units, you can't do that. Next, I'd like to demonstrate the software that was supplied with the V2 Plus. First, let's have a look and see which COM port the VNA uses. This is looking at Device Manager. Of course, I'm running Windows 10. Let's just go ahead and turn on the VNA. And we can see COM4 has been added. So that's the serial port that this device is using. Let's go ahead and launch their software. And this is what it looks like on the main page. So here we can select Device. Now I've just selected it, and you see the software is hung. I can't drag it. Oh, it just freed up. Let's try pressing Device again. And you see it's hung. And it just came back. Let's try it one more time. Device. I won't try dragging the screen at all. And now you can see it comes up with a menu selection. So here we could select COM4. And we also notice that there's another submenu here for sweep parameters. Let's go ahead and select the COM port. And we can see the device is now running. And notice the screen on the NanoVNA Plus. So once the unit has been connected to the PC, the only thing the LCD does is display this message. You can see it's quite a bit different than the original NanoVNA where the LCD was not disabled. You could also simultaneously send commands to the original Nano either through the touchpad or through the communications port. And really that's the reason I'm saying I could do without the LCD, the touchpad, or the push buttons because they're totally disabled the way I would normally run the unit anyway. So let's go ahead and we'll change the start and stop frequency. So again, I select Device, but again, you see the software is hung. So you have to select Device and wait. There, it came up. And you can see as I slid the mouse over, see it's hung again. Let's go to View, and you see it's hung. So I'm not sure what their software is doing. For me, this wouldn't be usable. Let's go ahead and we'll scan from 1 to 900 megahertz. and we'll do 101 data points. When I was playing around with this software, I tried to change the power level. It doesn't seem to have any effect with this particular unit. Let's go ahead and select OK. And what I'm going to do is just add a disturbance in the waveform, give you an idea how fast the thing is scanning. Again, this unit's quite a bit faster than what the original Nano was. One of the nice features with this is if we select calibration and then we can select kit settings, you'll notice that for each standard they support 2 models. The ideal model treats the short open and loads as perfect devices. With the S parameter settings, we could take a set of metrology grade standards and a lab grade network analyzer, and then we could characterize these standards. I looked to see if they offered any generic touchstone files for their calibration standards. I wasn't able to find anything like that. On the bottom, you can see they have a slider. This selects the location of the cursor. To run it through the calibration, we just select the short, the open, and the load. Again, I only spent a few minutes with the software. Once I realized that it would hang every time I tried to select one of the upper menus, I basically gave up on it and I started writing my own software. So when we first start up my software, the first thing it's asking for is a default file. This file contains all the settings for my software. The first time you run it, you may not actually have a default settings. In that case, the software will load up with whatever defaults it has built into it. So let's go ahead and we'll load up my defaults. And let's go ahead and we'll select link, and you can see this green LED illuminates. That tells us that the device is now linked to the PC. You can see it's discovered a NanoVNA V2 Plus 4. It's using Protocol 1, firmware version 1.1. Let's go over to Setup Diagnostics. In the far right, you can see the NanoVNA port, so we've selected COM4. This is the transfer relay on COM15. The stage COM port is used to control a mechanical stage that I use for TDR experiments. This selects whether I'm going to enable the stage or not. Below this we can select the units. Currently I'm defaulting to inches. You can also select meters, seconds, and samples. I also support up and down conversion. So for example, if you wanted to experiment at even higher frequencies than what the Nano could run, I do support adding external mixers. The upper sideband checkbox is allowing you to select whether we're using the upper or lower sideband for the up-down converter. So let's go back to the main page and let's select sweep. So once the PC is connected to the NanoVNA Plus, the VNA is essentially just sending up raw data to the PC. So right now the NanoVNA is not calibrated, and you can see looking at the Smith chart we're very close to the center. Let's go ahead and I'm just going to disconnect the cable. And you can see we're very close to an open. Before we get into this too far, let's just make sure that we have everything properly torqued. So for these first experiments, let's just use the standards that I came up with for the original Nano. Let's go ahead and we'll apply the short. And you can see that the unit isn't quite calibrated. So let me walk you through a basic calibration. Under Diagnostics, we go to Calibration Terms. And then under calibration standards, these are all the coefficients that you can assign to each standard. Currently it's selecting the custom ideal standards, and that's what we're going to be using, but let me select a different set of standards. So this is the Agilent 85033E. All these coefficients are supplied by the factory, and this software uses all those if they're available. You can see that this is the male set. We also have one for the female set. This is the 85032F, and again this is a female set, and this is the N-style male set for that kit. Now you can copy and add or change any of these standards any way you want, and you can save all these into that default settings file. So if you just select Save Setup here, that'll store not only any changes that you made to the calibration coefficients, it'll also store the units, the COM ports, and pretty much all the other settings for the software into a default file. Now again, you can have more than one default file. There's no limitation on that. Now the software is going to use whatever calibration standard you have currently selected. So if I were to calibrate the unit right now, the software is going to expect me to be using this Agilent 85032F kit. In our case, what we're going to be using is my ideal model. When I purchased my very first network analyzer, which was the 8754A, again that unit was built in the 1970s. When I wrote the software for it, I used the ideal models, and I used standards very similar to these to calibrate it. And I got very good results, but again, I was testing below about 1.5 gigahertz for all my experiments. And the numbers basically work out with that. So all I'm saying is you can get away with a lot as you start working at lower frequencies like this. Anybody that's taken apart an old AM radio, for example, with tubes in it, you realize like lead length, for example, isn't near as critical on a radio like that. As you start to look at FM radios, the layout becomes a little more critical, and at 400 megahertz it's going to even be more critical. Up to 1.5 gigs you can get away with something like this. Once you start pushing beyond that, I haven't had very good luck making homemade standards. So let's go back to the main page and we'll select 2-port cal. And it's asking, do we want to make a new calibration, load an old one, or cancel? Let's just load an old one. And you can see I store all these in a calibration directory. You can see this is for V2 Plus4. This is 201 data points. It's sweeping from 1 meg up to 300 meg. It's a 1-port Solt cal. So let's go ahead and load that up. And you can see our calibrated LED is now lit. Again, right now I have a short applied. And you can see our Smith chart is off in the far left. Let's go ahead and supply the open. And you can see we're on the far right. And let's just apply our load real quick. And there you have it, dead center. And you can see we're displaying 50 ohms on both cursors. If we wanted to perform a new calibration, we would select new. It's asking us to install a short on port 1. Again, port 1 being on the left. And we can install our open. And we can install our load, and then we install our through. And now it prompts us for where to save this data. We'll just use the default of calibration. Now if I had selected more data points, for example, when I run the calibration, the next time I load that calibration file, the software knows how many data points were used, and it'll reset up the software for the start, the stop frequency, as well as the number of points. Let's say I really only wanted to sweep from 10 megahertz, so I'm just going to enter in 10 in M for mega. You can see now there's an LED that's lit next to INTP cal. This means interpolation is enabled. So as long as you're working at frequencies that are within the range of the existing calibration, basically you don't have to recalibrate the unit. If we go out of range, so for example, let's go to 301 megahertz, and you can see now this calibration range error comes on. Again, we can go back within range and everything's going to be fine. So all the frequencies are in hertz. So M means meg, small k would be kilo. So let's go ahead and we'll put in a 1, for example. So 1 means 1 hertz, and so 1 hertz is below the 1 megahertz that we calibrated the unit. So you can see it's running interpolation, but it's also giving this calibration error. Let's go ahead and we'll try 1k with a small k. And now this is 1 kilohertz. For 1k, you could also say 1,000, for example. The software is always going to display the SI units. And let's change our stop frequency to 3 gigahertz. So again, this could be 3000 meg, for example, or we can just put in 3G. You'll notice that there's also a center frequency as well as a span. We can change the center frequency, for example, to 20 megahertz. We'll just put in a 20M, and automatically this is going to use a 4 megahertz span. If we go to transmission, you can see we're scanning from 18 megahertz to 22 megahertz. Let's just go back to 10 megahertz, and you can see we're sweeping between 8 megahertz and 12 megahertz. Let's change our span to 1 megahertz, and now you can see we're sweeping between 9.5 meg and 10.5. If I want to sweep between 1 meg and 300 meg again, all I need to do is select one of these two. So again, we're looking at transmission, and we have this through installed. You can see we're displaying roughly 0 dB from 1 meg up to 300 megahertz. Let's go ahead and we'll install our 10 dB attenuator. Again, with nothing applied, you can see we're down below about 70 dB or so. And you can see it's displaying roughly 9.95 dB or so. When we first looked at the original NanoVNA, I had made up several circuit boards to kind of prove how well that worked. I still have these standards. I've gone ahead and labeled them to kind of keep them straight. I've also added a couple to it. So this is kind of an interesting one. This is a homemade 50 dB attenuator. This is a 3-stage, I believe. Yep, looks like 3 stages. I made this to help somebody out on EEVBlog. They were asking about how to make a decent attenuator. So we can see roughly 49.5 or so dB. Here we have a 10 ohm 1% device. Again, we're looking at the shunt resistance, so You can see our nano is displaying 10.0, 9.9 ohms. Let's just go back to Smith chart. You can see our dot is basically at the 10 ohms. Again, for a 50 ohm system, it's a ratio of 5 to 1. And you can see our VSWR is reading 5.01 to 1 or so. This is a 24.9 ohm resistor. This should give us a return loss of 9.5 dB and an SWR of roughly 2 to 1. You can see the software is displaying a return loss of 9.44 dB and an SWR of 2.017. Here we have a 200 ohm resistor. Again, this should give us a return loss of 4.4 dB and a VSWR of 4 to 1. You can see our software is displaying the return loss at 4.36 dB and the VSWR is 4.048. Here we have a 499 ohm resistor. Again, this is a SWR of 10 to 1 and a return loss of 1.75. Again, the software is displaying 1.72 dB with a SWR of 10.08 or so to 1. Here we have a 1000 ohm 1206. Again, this should give us a SWR of roughly 20 to 1 with a return loss of 0.87 dB. Looks like the software is displaying roughly 0.86 dB with a VSWR of roughly 20.2 to 1. Let's go ahead and we'll save this to memory, so we'll select MS1. Here we have a 1000 ohm resistor as well, but this is an 0402 package. So these resistors should be the same except for the case. And notice that they are basically identical. Now if we tested these at higher frequencies, we'd probably notice a difference between the two. Here we have a 22 picofarad. You can see the software is displaying roughly 22.1 picofarads. This is a 220 picofarad. You can see our software is displaying roughly 217 or so. Let's just take our cursor B, and you can see at 100 megahertz we're displaying roughly 255 picofarads. Here we have a couple of inductors. This first one here is a 27 nanohenry. Now both of these are specified at 250 megahertz. So let's start with him. So you can see our cursor A is at roughly 26 megahertz and it's reading roughly 28 nanohenries, where the cursor B is at 260 megahertz and it's reading roughly 27.5 nanohenries. Let's just flip it to our 2.8 nanohenry part, and we can see the software is displaying 2.91 to 2.85 it looks like. And again, that's at 26 megahertz, and at 260 megahertz it's reading roughly 2.6 nanohenries. Again, I'm not sure what the tolerances are for a lot of these parts. Here we have a couple of tune circuits. This first one is a 151 nanohenries in parallel with a 66 picofarad. That should give us roughly 48 ohms at 50 megahertz. Let's just change this over to Smith chart. You can see we're at roughly 50 megahertz, so 50.33. It's difficult to actually get the cursors at the 0 point. We'd want to scan with a higher resolution. This one is 98 megahertz. This is a 82 nanohenry in parallel with a 32 picofarad. Again, let's just move the cursor close to that, as close as we can get it, and you can see it's displaying 95 megahertz. This one's 820 nanohenries in parallel with a 330 picofarad. Should give us a resonance of 9.7 megahertz. You can see that we really don't have near the resolution required to resolve this, but the cursor A is at 9.97 megahertz and cursor B is at 8.475 megahertz, and we're straddling it. Again, probably fairly close to the 9.7 megahertz that we calculated. So now instead of looking at the shunt impedance across port 1, let's look at the series impedance across ports 1 and 2. We'll start, this is a 100 picofarad capacitor, and we can see our software is displaying roughly 118 picofarads. I believe that that's a mistake on my label. This is definitely an inductor. It should be 100 nanohenries probably. Let's just see what we get. Looks like roughly 88. Now let's move closer to what the part is specified for. Both cursors are now at about 150 megahertz, and you can see it's now displaying roughly 107 nanohenries to 103. Again, if we were to install the through, you may remember the unit was displaying 50 ohms. Again, that's because the port 2 is indeed 50 ohms. So what I'm going to do is install a 50 ohm resistor in series, and it should display roughly 100 ohms. And you can see we're displaying 104 and 103, and again this is at roughly 130 to 150 megahertz. So here we have an interesting one. This is two 20k ohm resistors. These are 1206s, and these are in parallel, giving us 10k ohms. And now again, our port 2 is going to be 50 ohms. That's going to add to this 10k ohms. And you'll notice for our series resistance, we're reading roughly 8.3k ohms. But if we look at our shunt reading, we are getting roughly 10.0k ohms. Again, it's very important that you select the proper setup depending on the range of the device that you're trying to measure. This is a 4-to-1 RF transformer. Un means unbalanced to unbalanced, meaning it's ground referenced on both sides. You can see the circuit also contains a 3 dB attenuator. So let's attach port 1 to the output of our transformer. Cursor A, which is set for 4 megahertz, shows 411.7 ohms. Let's go ahead and flip it around. So we're now looking at the low impedance side of the transformer. And you can see it's displaying roughly 109 ohms. So roughly it's a 4-to-1 impedance match. So on the low impedance side, we're looking at roughly 50 ohms. And on the high impedance side, we'd be looking at 4 times that, or roughly 200 ohms. Of course, you may be wondering, why isn't this actually reading 50 ohms? Well, the high impedance port isn't being terminated right now. We're just going to attach a terminator to the back side of this. And you can see now cursor A is reading roughly 52.3 ohms. And of course, this is not a 50 ohm terminator. Some devices like an amplifier, you may want to characterize the input and the output impedance separately. That's where a full 2-port network analyzer would come in handy. Again, this isn't really a 2-port network analyzer. Like the original Nano, this can only measure S11, or the reflected signal off of port 1, or S21, where we're looking at the transmission. You may remember these from my previous videos. This is a couple of homemade transfer relays that I made for the original NanoVNA. This one was based on a couple of Maycom gas-ass parts. The other one is based on an Omron relay. These plug directly into the Nano. These were controlled off a USB to TTL adapter. I didn't have a lot of success with these, so down below here, this is a transfer relay from Transco. It's a model 700C70200. These are rated for DC up to 18 gigahertz, I believe. And again, the way this works, it's either transferring between these 2 ports and these 2 ports, or it's going between these 2 ports and these 2 ports. So it essentially allows me to flip the 2 leads. Now this particular relay runs off of 24 volts. So I needed a power supply for it. This is just a small boost converter. It's running off the USB bus. This is actually a 4069 or 4000 series inverter. It's just running as an oscillator. You can see I have a small inductor here for the boost stage. There's a few transistors. So this is also acting as a buffer to drive the 2 relay coils. This thing draws a fair amount of current. Because this is a latching type relay, the duty cycle for this is actually quite short. The only time you actually need any current is when you're changing the state. So what I'm doing is I'm charging up this large capacitor. You can see this is a 1000 mic 50 volt part, and then I just dump this across the relay coil to change its state. So this thing hardly draws any current at all. I think it's like on the order of a milliamp or something. The software uses the RTS pin to control the state of the relay. Looking at the software under Setups Diagnostic, you can see I have my serial port set to COM15, and I'm just using a FTDI to TTL adapter. Let's just go ahead and we'll select link. You could hear the relay click, and you'll notice that the transfer relay link is active. There's also this LED, it's called XFER Relay Error. The software expects the CTS pin to always be asserted. So in my case, I'm just hard jumpering that on the board. So the software doesn't have a lot of error checking. If it's successful in opening the COM port that you've identified as being hooked to a transfer relay, it's fine with it. It's going to start wiggling that RTS pin. So it uses the CTS pin as a way to identify that the transfer relay is actually attached to that port. So now let's go ahead and attach a short onto port 1. Of course the unit isn't calibrated, but we can see we're now picking up this short. And again, if I change the state of the transfer relay, we see the open on port number 2. Let's go ahead and install the load resistor on port 2. And we can see now we have a dot in the center for port 2. And again, port 1 has the short. Of course, the system has to be calibrated. And to do that, we have to place a short open load on port 1 and on port 2, and then apply a through between the two ports. Now that the software knows that it has this transfer relay attached, let's go ahead and select 2-port cal. We'll select new. See, it's asking for short on port 1. Now it's looking for an open on port 1 and a load on port 1. Now it's changed the state of the transfer relay, and it's asking for short on port 2, the open on port 2, and the load on port 2. Now we go ahead and install the through. And now it's asking us again, where do we want to store this calibration? We'll just cancel out of that. So this is our calibration. Let's go ahead and load one up. So again, we'll do 2-port cal. Let's do old. This one is for the V2 Plus4. You can see it's 401 data points, and it's sweeping between 1 and 50 megahertz. 2P means it's a 2-port. You may remember this device. This is my T-check. Again, you can think of this as nothing more than a T with a 50 ohm terminator off the one leg. Of course, at 50 megahertz, you probably don't want to have a stub like this hanging off of it. And in this particular case, we've used this circuit board to cal the VNA, so our T-check is built up on the same type circuit board. We'll go ahead and install this between ports 1 and 2. Let's go ahead and select T-check. It's prompting us to install the T-check adapter. Now the vertical axis on this is in percentage, and our error is between 92% and 105%. You'd like to see this below plus or minus 10% error, so we have a very usable alignment. If we go back to impedance, you can see we have a dot over here at roughly 25 ohms. Of course, we have 250 ohms in parallel. Now that we've calibrated our VNA and we verified its accuracy, now let's go ahead and install our short on port 1 and install our open on port 2. Let's go ahead and double our stop frequency to 100 megahertz. Of course, we have this calibration error and it's running interpolation. Now let's run a 2-port sweep. Again, the software automatically stores port 1 to memory 1 and port 2 to memory 2. So if we go ahead and remove our short on port 1, and let's go ahead and attach our attenuator. This will give us roughly 50 ohms. Again, we can see the original port 1 data in yellow and the port 2 data in purple. We can display all this data simultaneously by selecting Advanced. In the upper left, we can see 2 Smith charts. One's for S11, the other for S12, and then we have a graph for each of the 4 S parameters. We also have a graph in the upper right for the SWR. This is a 5-pole 12 megahertz low-pass filter. And on the other side of this, I've placed our T-check. Let's change our stop frequency back to 50 megahertz. And now let's select 2-port sweep. So now let's go ahead and select impedance rectangular. And we can see what the impedance looks like on the 2 different ports of our device. Again, if we select advanced, this is again looking at all 4 S parameters for our test device. If we select transmission, again, this is a 12 megahertz filter. Let's go ahead and move the 2 cursors to the 3 dB point. And you can see it's measuring, what, 12.5 megahertz? Again, the way the software works, when you select the cursor minus 3 dB, it's essentially treating the device as a bandpass. So you can think of cursor A being on the rise and cursor B being on the fall. So here we have a 3.68 megahertz crystal. Let's try to characterize this using the V2 Plus4. Again, we have a small test fixture that I've made. If we follow from the connector on the left, there's a small 3 dB attenuator. This connects to the input of this RF transformer. This is a 4-to-1 impedance match, so we'll take 50 ohms up to 200 ohms. That'll feed to one side of this fixture. On the other side, we go to another 4-to-1 transformer and then back to another 3 dB attenuator. I've used this fixture to look at crystals in excess of 20 megahertz, and again I've compared the results against other network analyzers using the same fixture. Again, the only purpose of these two transformers is to get us closer to the impedance of what this crystal is. Let's go ahead and set our center frequency for 3.68 megahertz. This main spur, this is the fundamental frequency of our crystal. Let's just zoom into this a little bit. We'll put in 1 megahertz. So let me just demonstrate a couple of features while we're at it. Here we have an old vintage crystal. This is rated for 3,713 kilohertz. Let's go ahead and replace this into our test fixture. And you can see that's actually changed the peak location. We'd expect that. Let's go ahead and pick peak center. What that'll do is take whatever the maximum signal is with the current graph type, and it'll move it to the center of the graph. So let's zoom in on this a little further. Let's just go ahead and put in 100 kilohertz. And now let's change our crystal back to the Fox part. Again, we can see our peak has moved over, and let's go ahead and hit peak center again. So let's go ahead and zoom in on this peak. We'll just press zoom. Actually, let's just go ahead and zoom out on this a little bit. Let's plug in 50K, and you can see all these spurs. This is because of this network analyzer. With every other network analyzer I have, this data would look very smooth. Again, let's just go ahead and zoom back in. You can see all these steps. Again, this is not normal. What we can do is select advanced. The graph in the center of the screen is the center frequency for a crystal. You can see this is roughly 3.68 megahertz. You can see we're resolving well within 1 hertz resolution. Let me just take my fingers, and I'm going to touch this crystal real quick. I'm going to let go of it. That's the drift due to the temperature of me just touching the crystal. Once I plug the crystal into the fixture, I let it become stable on this graph before I collect any data for it. The software can calculate the capacitor C0 automatically. Let's go ahead and select that. What we do is, in this case, I'm running the crystal at 1 megahertz. I move it far away from the resonance point of the crystal. It's calculated a TRC of roughly 4.581 picofarads. Let's go ahead and clear this graph again. In the lower graph, this is a histogram of the center frequency. Again, you can see our part is still drifting. Let's say we wanted to record that, so I'll just press record. Let's go to log data, and we'll just store this in the record.bin file. We'll let this thing run for a little bit. So on the left, we have the series frequency, the bandwidth, the attenuation, the loss resistance, the crystal's Q, the loaded Q, the inductance, and then the capacitance. This manufacturer info, what you would normally do is fill this out. So for example, I'll normally mark all the crystals that I'm going to characterize. I'll just write on them with a magic marker, and I'll put that number into this box here. For brand, I just enter in the manufacturer's name, in this case Fox, and then the model number of the crystal. Once I've collected the data, I just hit Save Data, and then it asks me where I want to store that. So we'd go to Crystals directory, and sure, we just use the default. Let's go ahead and turn off our recording for now. Once I've collected all this data, I go over to Crystal Sort. So here I enter in the number of poles for the crystal filter I'm trying to build, and then I select Sort Data. Unfortunately, we've only looked at one crystal. Let's go ahead and select this other database. So this is all the Fox 3.68 crystals that I characterized, and what this does is it sorts them, and then it highlights the 4 best crystals that I can use to build this crystal filter. Look at CM, so 11.27, and LM is roughly 165, down to 148 or so. Looks like the lowest CM is about 11. Now look at this same crystal. You can see the CM is roughly 8.5, and LM is roughly 218. So this is one of the crystals that I had actually characterized out of that group. And again, that was done with multiple network analyzers, and I also used 2 other methods to make those measurements. All those were fairly close. So yeah, basically you can't use this V2 Plus for any kind of narrowband measurements like this. Let's go ahead and select Surface, and now let's go ahead and add a waveform, and let's select the data that we just collected. You can see it kind of looks like a vertical line. What we want to do is select Narrowband Zoom. This is looking at the resistance to the input of the fixture. Let's have a look at S21 mag. And you can see this little bit of movement. This is where I've touched the crystal. Again, looking at our parameters here, This is the notch where I've touched the crystal, and then you can see it heating back up. This graph can be helpful when looking at long-term tests. Again, if there's a slight drift or something with the device that I'm looking at, this allows me to visually see that fairly quickly. This is our 12 megahertz 10-pole homemade crystal filter. Let's go ahead and attach this between port 1 and 2. We'll change our center frequency to 12 megahertz. Let's go to transmission, and here we can see our filter. Let's go ahead and zoom in on this a little bit, and we'll go ahead and recenter the peak. So I've characterized this same filter using the original NanoVNA. I also have an old HP3589A, and you can see the data for those two instruments is very similar. Hopefully that makes it very clear that this V2 Plus4 can't be used for narrowband work. Here we have an interdigital filter. This filter has a much wider bandwidth than this crystal filter that we just looked at. Let's go ahead and we'll move our cursors to a 3 dB point. You can see our distance between cursor B and A is roughly 135 megahertz. This software has the ability to save a touchstone file. We do that by selecting S2P save, and we just use the default file name, for example. We can run the same test with the original NanoVNA, and we can use AppCad to import multiple touchstone files, and then we can see how these two network analyzers compare. Alright, this is looking at AppCad. One of the features of this software is to display S-parameter data. Here's the data that we collected for a filter using the NanoVNA. This is 101 samples, and you can again see we're sweeping between 800 megahertz and 1300. Let's compare this against the data for the V2 Plus. Right in here you can see the two start to diverge at about 20 dB down. Of course that's at 1150 megahertz. Again, the original NanoVNA I wouldn't recommend using once you get up above about 300 megahertz. So let's compare this against my Agilent VNA. So again, this is looking at the gain. Up here we see the original Nano compared to the V2 Plus4 in purple, compared against my old Agilent VNA in blue. Again, let's have a look at the phase, and let's just zoom into this a little bit. You can see the phase for the original Nano isn't really tracking with the other two. Let's just go ahead again and we'll turn that off. And here again we can see the phase for the V2 Plus4 fairly closely tracks against our old Agilent. This is again looking at the gain. Let's just pick one of these lobes and zoom in a little further. And you can see once we get above about 75 dB or so, these two network analyzers track really close. Let's look at the phase in just this area. The two definitely look very similar. Again, for $150, if you're wanting to play above a gigahertz, I would say this does a fairly decent job. Certainly much better than what the original Nano could do. The main reason I would expect anyone to purchase the V2 Plus4 would be to run at the higher frequencies. Again, they specify these units to operate up to 4 gigahertz. Now this particular unit can pull useful data off at about 4.4 gigahertz. Unfortunately though, like I said, most of my experiments that I've ran are all sub about 1.5 gigahertz or so. And up until recently I really haven't ran any experiments above those frequencies. So unfortunately I don't have a lot of devices we can test. But I do have a few experiments I'd like to run. So remember the first thing I talked about, these two 1000 ohm resistors. Again, there's definitely a difference in the package. We couldn't detect it at the low frequency, so we were sweeping at 300 megahertz. What we're going to do is open up a new calibration file. You can see this last calibration file. This is for the V2 Plus4. It's 401 data points, and it's scanning between 2.5 and 4.4 gigahertz. So let's go ahead and load this. And we can see the unit is now scanning between 2.5 gig and 4.4 gigahertz. Let's go ahead and we'll install our 1206 resistor. And let's hit save to memory 1. And now let's install our 0402. Notice what's missing? This entire loop right here. So again, to be clear, I'm not suggesting that this is how you would measure a resistor like this, but you'll notice that these two boards are basically identical. They're using the same connectors, same circuit board, the only difference being that one little component there. For this next experiment, let's just try two identical resistors. These are both 49.9 ohms. They're in a 1206 package, and they're from the same section of tape. First thing I'd like to do is load a different calibration. So let's go old, and this time what we're going to do is load our 1 megahertz to 900 megahertz cal. Let's just start with the resistor. It's mounted onto the SMA. And we can see this little tiny stub out here. Tell you what, let's just change this to impedance rectangular. So you can see we're sweeping between 1 megahertz and 900 megahertz. And it's starting off at roughly 50 ohms and it's working its way up to 54.8 ohms. Let's go ahead and we'll store that into memory. And let's go ahead and put in the other resistor. The circuit board version is up to roughly 58 ohms, where the one that's mounted to our SMA connector is down at about 54 ohms. So if it's not the resistor, what's really changed? Well, there's actually quite a few differences. The connector isn't quite the same. I've got the dielectric of this circuit board under here, but the primary difference is look at how far this resistor is located away from the center pin versus the one that's mounted directly to the SMA connector. That distance will make a big difference in this measurement. We can adjust for that by changing this port extension. So let me just adjust that down a little bit, and you can see they're getting very close now. So let's save this waveform to memory 2. What I'm going to do now is remove our little test board, and now let's attach our calibration standard, and you can see it's very close to 50 ohms. Again, I had this small extension on here, so you can see there's still quite a bit of difference between these two. So if you need to compensate for small errors like this, that's one way to do it, is to just use that port extension. Again, if we go back to setup and diagnostics, you'll notice that there is a delay for all these standards. And you'll notice that I have all these set for 0, and again that's because I'm treating all of my standards as being ideal. So it's possible, for example, if you had a circuit board like this and you were trying to test this component, and let's say your calibration standard looks something like this, so you need to compensate for that reference, it's possible for you to go ahead and change that delay for your standard. Again, I wouldn't recommend that unless you actually had a real network analyzer along with metrology grade standards and you were going to try to characterize them. And again, I'm not suggesting that anyone should take a metrology grade standard and attach it to one of these devices, at least not with the connectors that I'm showing here. Of course, my buddy Flipper would get on me if that's all I showed was a couple of resistors. So let's look at something a little more complex. What I have here is just some 3M copper foil tape. You can see the thickness of this tape is 1/1000th of an inch. And I have a piece of FR4 material. You'll notice that this is single-sided. You can see the thickness of this board is roughly 56 thousandths. So what I'd like to do is use this copper foil and some blank circuit board material to make up a couple of experiments. This is a program called AppCad. This is essentially a microwave calculator. Let's select AppCad, and then we can go to transmission lines, and let's go to microstrip. The first thing we have to do is select our board material. We are going to select FR4. We'll say 1 gigahertz, that's fine for now. Unit length, we'll just leave that for mils. So we said our circuit board was 55 thousandths thick, and we said our foil tape is about 1 thousandths thick. Let's go ahead, we'll plug in 100 or 0.1 inches and calculate Z0, and you can see that gives us an impedance of 50.12 ohms. Let's say we wanted to get 100 ohms, for example. Let's go ahead and change the width to 22 thousandths and calculate Z, and you can see that gives us 99.5 ohms. Let's say we wanted 25 ohms. If we select 278 and calculate, and that gives us 25.0 ohms. So here I've made a little test board. On the ends you can see I just have 2 SMA connectors soldered to the ground plane. I've got 2 feed traces. These are 100 thousandths wide, and then I have cut away this area with an X-Acto knife. I don't know, it's a little tough to see through the tape, but there you have it, roughly 278, and you can see we're in the ballpark. So let's go ahead and hook this up to port 1, and for now let's just leave the other side floating. Again, when you first start the software, it's going to pre-program the Nano for a center frequency of 10 megahertz with a 2 megahertz span. Let's go ahead and just select the 1 megahertz start frequency, and you can see now how we have these several circles. Again, this is now sweeping between 1 and 300 megahertz. So let's go to 1.5 gig. You can see we've got a lot more circles now around the Smith chart. Now let's go ahead and select the TDR measurement. And you can see at the very beginning, it's starting off at 50 ohms. And you can see it rises up to about 90 ohms, and then it looks like it dips to about 25. Now again, let's look at our circuit. We start off at roughly 50 ohms. We transition to this really fine piece of copper, and again, that's giving us roughly 100 ohms. Then we go back to 50 ohms. Then we have this very wide section of copper, which is giving us our 25 ohms. So that 25 ohms is this dip. Again, there's not a whole lot of resolution here, but we can correct that. So let's go ahead and we'll take this thing up to 4.4 gigahertz. And while we're at it, let's change our start frequency down to 100 kilohertz. Now let's have a look at our TDR measurement. You can see now the edges are starting to look almost square. We can zoom in on this. Let's do auto scale X. Now you can see we have a lot more detail. We start off again at 50 ohms. There's a little bit of bump in the data. It rises to about 93 ohms or so. And then it has a sharp transition down to about 25 ohms. You'll notice that the full width half height for these two is roughly the same. Of course, the length of these two trace sections is roughly the same as well. Let's just take my fingers and I'm going to move it over the top of the thinner trace. And you can see what effect that has on the 90 ohms. So that's one of the benefits of having a higher frequency network analyzer, is if you're doing TDR measurements, you can get a better view of what your traces are actually doing. Again, if we want to increase the number of data points, we can do that. So let's just go to 401 data points. You can see our circles are a lot smoother, but you can see it really doesn't have any effect on our measurement. Again, by changing the number of points, it's basically changing the length of the circuit that I'm able to measure. It doesn't have anything to do with the resolution of the measurement. So let's have a look at another circuit. These are both made on the same type of FR4. As a matter of fact, all the circuits I'm going to show you are made on the same type of FR4. Again, all these traces are 50 ohms. You'll notice that this one just seems to go off to nothing. This is known as a stub. It's not been terminated. It's just hanging out there in free space. So what this acts is a notch filter. So in this case, I'm going to have two notches, one at F and one at 3F. So what we're looking for is to have this notch show up at about 1.25 gigahertz or 3 times that, or 3.75 gigahertz. So what we do is we take the speed of light and we're going to divide that by the frequency that we're interested in. So that gives us a wavelength of 0.24 meters. Stub should be 1/4 wavelength. That gives us 60.2 millimeters. Again, for the FR4, it has an ER of 4.6. So what we do is we take 1 over the square root of ER, and that equals 0.47. We multiply that by our 60.2 millimeters, and that gives us 30 millimeters. And again, that's the length of our stub. So let's go ahead and we're going to attach this between our two ports, like so. And now let's go ahead and have a look at our software. We'll select this to transmission, and you can see there's two definite notches. So let's bring our cursors to the center, and let's move cursor A down into that first notch. Right there you have it. So cursor A is at 1.243 gigahertz, and we were targeting 1.25 gigahertz with this design. Let's have a look at our other notch. So again, we'll take cursor B, move that down into the notch, and we can see it's at 3.784. Again, we were looking at 3 times 1.25 or 3.75. So fairly close, again, just for cutting up some foil and sticking it to a circuit board. So let's have a look at a bandpass filter. Again, all of the traces shown here are 0.1 inches wide or 50 ohm impedance. So in my case, what we're looking for is a center frequency of 2.5 gigahertz. Again, we take the speed of light divided by that. That gives us our wavelength of 0.12 meters. We divide that by 4. That gives us our 30 millimeters. Again, the circuit board material has an ER of 4.6. We take 1 over the square root of that. That gives us 0.47. And again, like before, we're going to multiply that by our 30 millimeters. That gives us a 14.1 millimeter stub. And so let's just switch our caliper over to millimeters, and let's have a look. And you can see we're fairly close to 14.1 millimeter for all these stubs. Now in this case, all these stubs are terminated to ground. So let's just look at from our ground plane on the back to the center conductor. And you can see it's basically a dead short. Again, we can check it up on this side as well, and you can see it's a dead short. So might come as a surprise that with all these conductors being shorted to this ground plane, that any signal at all is going to get through this. Let's have a look. You can attach either side to port 1 and port 2. And now let's have a look at our software. And now let's look at our 3dB point. So cursor A, it looks like, is at 1.81 gigahertz. And you can see we had calculated an F1 of 1.8 gigahertz. F2 should be at 3.3 gigahertz. And you'll notice that the software is calculating 2.86. Again, we've got quite a bit of noise in here, but you'll notice one thing. I've never calibrated this system at all. This is running totally uncalibrated. So let's just take our cursor and we'll drop it down roughly here, and let's see what we get. So now we're getting 3.41 gigahertz. So if I were to actually calibrate this unit, it would probably come up fairly close to what we've calculated here. So it's definitely possible to build some fairly high-speed circuitry just using some copper foil and some circuit board material. So I was in the process of editing this video. Unfortunately, with the unit uncalibrated, I was basically eyeballing where to put the cursors, so just sort of fudging the data, and I thought it was probably worth it to go ahead and calibrate it and show what it really looks like. So again, we're using the original cables that came with the NanoVNA Plus, and I'm using the standards that are shown here. And again, to be clear, I'm not using the original load. I'm using this part from mini circuits that I've hand sorted. Other than that, and being able to now torque the short, there is no other differences. So looking at the software, you can see I've set it to 1024 data points. I was trying to get us a pretty good resolution. You can see I'm also sweeping between 1.5 gigahertz and 3.8 gigahertz. You can see our filter now looks quite a bit flatter. Now let's go ahead and set our cursors to the 3dB point. You can see cursor A is now reading 1.83 gigahertz, and cursor B is reading 3.35 gigahertz or so. We had calculated 1.8 gigahertz for F1, and F2 should be 3.3 gigahertz. In the upper right, we're displaying the difference between cursor B and cursor A, so you can see this thing has a bandwidth of roughly 1.52 gigahertz or so. So the filter is not only a lot flatter, the software is actually calculating the right values. Again, this is all automatic. If we go ahead and select cursor center, you can see again it brings both cursors to the center of the screen. And let's go ahead again and select cursor minus 3 dB, and you can see it snaps both to the 3 dB point. Now again, that's not 3 dB point off of 0, that's 3 dB point off of the peak, which happens to be this location right here, and then we're measuring 3 dB down from that. The other thing I'd like to show, as long as we have this thing set up, I'm going to leave that running live, and let's just move the filter and let's see what effects those cables have. As a matter of fact, let's just go ahead and store this into memory 1. And you can see basically no effect. If you're a hobbyist and you're just trying to get started playing around at these higher frequencies, I think that this is really a perfect product. Again, sure, it can't do narrowband measurement, but there is a fix for that, and that's just to go out and buy the original Nano. As long as you're willing to overlook that small problem, I think this thing is a very good deal. Alright, let's get on with the video. What I have here is a couple of antennas. So one of these will be a transmitting antenna, the other one a receiving antenna. Again, it's the same circuit board material, so it has an ER of 4.6, and again it's 55 thousandths of an inch thick, and we'll design these two antennas to work at 2.3 gigahertz. So what I did in this case is I wrote a little LabVIEW software to run the numbers for me. Again, you can see our ER of 4.6. Here's the thickness of our circuit board. Again, we're looking for a target frequency of 2.3 gigahertz. Where we terminate into the antenna, we have this little gap that's defined as R. We've also defined the length of the pad as well as the width. The software calculates roughly 40 millimeter width and a 30 millimeter length. So let's have a look. Again, this is our width, and you can see we are roughly 40 millimeters, and you can see our length is roughly 30 millimeters. And R again, which is the length of this little gap, is roughly 10 millimeters. So unfortunately, you saw as we ran this filter, not having the unit calibrated, we weren't able to actually look at the two side lobes. So to look at these antennas, we're going to have to perform our calibration. So I've actually done that off screen. I'm just going through now and cleaning the connectors. Again, I just use alcohol for this. I've had some people tell me that they use, I don't know, some kind of contact cleaner. I was thinking, wow, that's just crazy talk. If you look at the manufacturers of the connectors, they'll tell you how to clean them and how to care for them. Somebody recently had asked too, they said they didn't understand why I wouldn't want to touch a connector with my bare fingers. Of course, you see me do that throughout the video. These being our standards here, I'd rather not try to touch them, especially these parts right here. These are tough to get in and out. Again, what you probably want to do is try to find yourself a set of ignition wrenches. You can see how thin these are, and these will fit right inside of these slots of the various connectors. I would get yourself some gloves anytime you're handling these. Basically, again, it'll keep your dirt off of your fingers from contaminating the threads. Again, these are a fairly cheap set, but that's no reason not to treat them with enough care where they last for a while. With my real network analyzer, I clean the connectors between each use. And I typically do the same thing for the Nano. The one thing I don't do is, you'll notice again, I had a whole box of parts for the Nano. I tend not to use the same parts between the two network analyzers. If there's a part that I want to analyze on one of the other network analyzers, I have some connectors that I use specifically for that. You can see some of the grunge here that we picked up. Alright, let's go ahead and we'll connect our antenna. Again, you can see we are now sweeping between 1 and 3 gigahertz. Let's go ahead and switch this over to standing wave ratio, and there is a definite notch right here. So let's just move our cursor down, and you can see that's right at 2.355 gigahertz, so very close to our 2.3 gig. You'll notice that our SWR is off quite a bit. Let's just store this to MS1, and let's have a look at our other side. So you see that the two are very comparable. They both have roughly the same resonant point. Let's attach port 2 to the second antenna, and let's select transmission. Let's just clear out our memory, and you can see there's a definite peak now, and again that's right at 2.34 gigahertz. And what's happening, of course, is we're transmitting from this pad over to this pad across the circuit board. Let's go ahead and we'll store our reference. So it's stored in MS1. Let's take this other piece of circuit board and just wedge that between the two of them. You can see it's dropped about 10 dB doing that. Let's just try shorting the two out. You can see now it's very broadband. Of course, we'd expect that. Essentially all that we're doing now is we have two capacitors coupling across the backside of this plate. This was a very low cost set of attenuators. You can see we have the through, a 10, 20, and 30 dB. What I'm going to do is attach the 30 dB attenuator between port 1 and port 2, and you can see at 4.4 gig this thing's reading up at about 24 or so dB. Let's just go ahead and save this. So if we didn't want to do a full-blown calibration, one thing we can do is try to normalize the data. So let's go ahead and we'll attach their through, and ideally this should read 0 dB. Of course, you can see it's not quite flat. It drops down to about a -4 dB at about 3 gigahertz. So what we can do is just store this into the reference, and now let's select channel minus reference. You'll notice now it's basically reading within 1 dB from 1 meg up to 4.4 gigahertz. You'll also notice that our saved memory has changed. That's because this software will take that reference value and subtract it off of any of the memories that are stored. So if I reinsert our 30 dB attenuator, you can see the signal is exactly the same. Of course, we haven't actually calibrated the Nano. Let's just install a Midwest microwave attenuator. Again, this is 30 dB. You can see it's within 1 dB up to about 3 gigahertz. And you can see between 3 gigahertz and 4.4 gigahertz, it varies about plus or minus 3 dB. So you can't always use normalization to correct for any errors. Let's go ahead and we'll load a calibration. Again, we'll use the 401 data point, 2.5 gigahertz to 4.4 gigahertz. With this network analyzer, once you get above about 3 gigahertz, there's quite a bit of leakage between port 1 and port 2. Normally when you're creating the models, you won't take that into account because you can actually add noise to your measurement by adding that coefficient. Let's select Setup Diagnostics, and under Calibration Terms, you can see this Leakage Terms checkbox. This is enabled right now. Tell you what, let's just save this before we do anything, and now let's enable the leakage terms. And you can see this has made quite a bit of difference. It looks like we're now within about plus or minus 1.5 dB all the way up to 4.4 gigahertz. Let's just save that to memory too. And now let's reinstall our low-cost 30 dB attenuator. And you can see it's a little better, but it's not near as good as our Midwest microwave part. You can see up at about 4.4 gigahertz, it's reading about 24 dB. Now again, as we start working below 3 gigahertz, I haven't found a need for that leakage term coefficient, so that's something you just want to keep in mind. This is looking at my linear stage. On the far right, you can see we have a stepper motor. This attaches to a ball screw. Attached to the ball screw is a piece of airline coax, and the airline is attached to port 1 of the Nano. And we can use the stepper motor to change the length of this. You can see the back side of the airline is not terminated. You can see we're sweeping between 1 megahertz and 4.4 gigahertz, and we've selected our stage. Again, that's done through the Diagnostics menu, and then in the upper right you can see where we set the COM port, and then we just select the stage checkbox. Under Advanced, this particular stage will travel 0.1 inches for every 2,048 steps. So we're going to move it in increments of 205 steps, or roughly 10,000ths of an inch, and we'll do that 150 times. This top readout is our travel in inches. The right is going to be in millimeters. We also plot the length of travel in inches, and the center graph is showing a histogram of each unit length. So again, in our case, we're traveling 10,000ths of an inch, so this is going to show us the variance of that 10,000th step. And again, that's according to what the Nano provides. Again, each one of those movements is 250 steps of the stepper motor. That's causing our piece of airline to move about 10,000ths of an inch. Probably a little difficult to tell, but this is the length of the travel that we're talking about. We're trying to get roughly 1.5 inches, or about here, and the slide is currently at this location here. And you can see we're at roughly 1.5 inches. So looking at our software, you can see the Nano reports that it's traveled 1.492 inches. Again, we were targeting 1.5 inches. On the left, we have the minimum and the maximum step size, the mean step size, and the standard deviation of the step size. So the average step size was roughly 10,000ths, and the standard deviation for the step size is roughly 0.00091 inches. You can see the min and max is between 7 and 14 thousandths. If you look at the histogram, there's definitely some noise. This is pretty decent compared to what the original Nano could do with this same test. But again, with the V2 Plus running at 4.4 gigahertz, we end up with a lot better resolution. In the bottom graph, we can see the total travel. If we kind of zoom in here a little bit. Again, this is looking at the TDR signal for each of the increments. And visually, just looking at them, you can see, again, there's not a lot of difference in the spacing. You can tell, like here, there's a little bit of a gap, and then it gets a little tighter. For a $150 unit, I think it does fairly well with this test. One of the videos that I made for the original NanoVNA was demonstrating how to measure the SWR of a small antenna. So I had a viewer ask me a question about that. What they're claiming is they had a radio station located very close to their home, and that radio station, of course, that's transmitting some power at some frequency, and what they're claiming is that that radio station is interfering with their SWR measurements of their antenna. Now again, the NanoVNA is going to be very selective when it makes these measurements. So for example, let's say they're looking at 20 megahertz and this thing is transmitting at, let's say it's 1 megahertz. That signal isn't going to get through to this 20 megahertz measurement. But now let's say that they're measuring between 500 kilohertz and 2 megahertz. And now all of a sudden what's going to happen when we're looking at the SWR is we're going to see this disturbance. So the question is there a way to mitigate this problem? And I believe that there's a pretty simple method that you could use. So here we have my antenna simulator. All we have here is a 20 dB attenuator that I rebuilt recently. You can see I've also mounted this bracket to the side with a couple of cooling fans. I've actually had this thing running for about 2 hours at 200 watts. The attenuator was originally rated for 1 gigahertz. The parts that I have in there now are rated for 1.5 gigahertz, and this thing performs very well up at those frequencies. We won't be using it that high today. On the back side, you can see I just have this coupler, and that's followed by 20 dB more of attenuation. So the total attenuation of this system is 40 dB. So what we're going to do is we're going to attach the nano onto this port. We're going to measure S11, and then we're going to take a signal generator, attach it to this port, and we're going to inject a signal while we're trying to measure the S11 of this attenuator. Let's just go to transmission real quick. You can see we're scanning between 9 megahertz and 11 megahertz. Again, these are the defaults for the software. You can see I've gone ahead and calibrated it. Let's go back to Smith chart, and you can see the dot is basically on the far right for an open. Let's just go ahead and we'll attach our 50 ohm load standard. And again, we can see a dot dead center of the screen. If we select rectangular impedance, you can see it's reading roughly between 50.05 and 49.98 ohms. So what we're going to do is attach our large attenuator to port 1, and you can see it's reading roughly 50.2 down to 50.14. So let's go ahead and switch that to standing wave ratio, and you can see it's displaying roughly 1.005 or so. Now unfortunately most antennas are not that good, so what we'd like to do is simulate a more realistic antenna, and we're going to do that by inserting this little device. This is a 230 ohm resistor. It's actually 4 1206 resistors in parallel, and again they attach to the outside shield, so it's essentially 230 ohms between the center conductor and ground. This will create an SWR of 1.22 to 1. It should also cause a change of about 20.1 dB. So let's go ahead and attach that. Again, we'll just go between the network analyzer and our load, and there you have it. So 1.211 or so to 1. So that's the start of our antenna system. Now again, the question is, if we introduce a signal into the back side of this attenuator, will we pick that up in this SWR measurement? So this cable is going off to our RF generator. I'm currently outputting a signal right at 10 megahertz, and it's minus 10 dB, and this is going through a 40 dB attenuator. Each one of these is 10, and again this one is 20. And you can see with the nano we are definitely picking that up in our SWR measurement. Again, that's probably a fairly high level, but if you had a radio station maybe right down the road from your house, you could probably pick up a signal like this. So here we have a homemade directional coupler. Of course, if you're playing with a VNA, I assume that you already know what a directional coupler is. This one happens to be made out of these TDK ferrite cores. This is an RH series. These are an HF70 RH14. We'll attach port 1 of the nano to the input of our directional coupler. And then I also have this step attenuator. So we're going to attach this to the reflected output, and let's attach that to port 2 of the NanoVNA. Normally when you're looking at S11, you're doing that all through port 1 of the nano, but in this case what we're going to be doing is looking at the reflected signal off of port 2. Currently our step attenuator is set to 0 dB, and we have nothing attached to the output of the directional coupler. You can see the nano is reading roughly 17.6 dB down. Now let's go ahead and attach our load. And you can see at 10 megahertz the nano is now reading roughly 48 or so dB down. Next thing I'd like to do is just remove our little disturbance, and we're going to attach our directional coupler directly to our load. So again, we have our power attenuator going to the output of the directional coupler. We have the reflected port of the coupler going through this step attenuator, going back to port 2 of the Nano, and then we have port 1 feeding to the input of the directional coupler. Again, we can see the disturbance off of our RF generator feeding into this measurement. Now let's go ahead and add our disturbance. And you can definitely see the disturbance from our signal generator. Let's go ahead and zoom in on this a little bit. So I'm going to change the span to 1 megahertz. And again, our software is now showing that we're using interpolated data. Let's take it into 50 kilohertz. And now we can really see this interference. Let's just go ahead and store that. And now the next thing what I'd like to do is add an amplifier. So we're going to place that between the Nano and this directional coupler. Again, just to make this a little clearer, on the left I have my Nano. This is port 1 and port 2. Port 1 now is going to go to a power amplifier. This isn't in there right now. This goes to a directional coupler and then into this bad mismatch, which again is causing a 1.2 to 1 SWR. And then that goes to a 40 dB attenuator and then to a RF generator. And this is outputting currently 10 megahertz. Again, I don't know what the radio station that he's talking about is putting out. He didn't elaborate on that. But again, this is outputting a signal into this attenuator. So of course this is disturbing our measurement, just like it would in real life. And then we're looking at the reflected signal back on port number 2. And that's of course going through this step attenuator. So what we're going to do is attach this power amplifier, and we're going to change this attenuator to compensate for that. So again, here's our power attenuator to the directional coupler, and the input of the coupler attached to our power amplifier, and the input to the power amplifier feed into port 1 of the Nano. Again, port 2 connected to the step attenuator going back to the coupled input. And let's go ahead and we'll adjust our step attenuator. Get this fairly close to our original signal. And now you can see that the signal is very flat. I would imagine for most of you, this isn't really going to be much of a surprise. Obviously, if we have a low enough signal out here and a high enough signal over here, the signal to noise ratio will be quite poor. By introducing an amplifier and then looking at the reflected signal, we can raise the amount of power that's going into this side of our attenuator, and then we can overcome this signal. So just an interesting little experiment. If you're interested in working above 300 megahertz, I would definitely recommend buying this V2 Plus4. Again, it's a very fast analyzer compared with the original Nano, and you can see we can actually collect some decent data up to about 4.4 gigahertz with this. Of course, I'm sure a lot of you are going to be asking about the software for this again. So what I've done is I've set up a GitHub account, and I'll place the link for that in the description. I'll also include a link to the EEVBlog site where I've been posting about the Nano. I've started to work on the documentation for this software, so if you have comments about the software or suggestions, feel free to post them there. Well, I think that's going to be it for this video. I hope you enjoyed it. So stay safe, and we'll see you in the next video.